So what we're going to do today is we're going to do the last of the preliminary lectures before really getting into linear programming. So by Wednesday, we will start off by getting to the diet problem. And at this point, I'm going to assume your programming is fine. I'm going to assume your linear algebra is fine. I want to revisit one more algorithm which you may or may not have seen. I know there's a great debate on it, which is available legally and illegally through various means. Since it involves several professors here, I have to be very careful about providing links to it. Anybody know what debate I'm thinking of? Not E versus pi. I'm sorry, no, not Lucky Hamantashen. That's a no-brainer. Lucky is definitely inferior to the Hamantashen. Nope, not integral derivative. They've got one more. Did somebody say Red Sox? Yeah, that's also not debatable. At least not in this class for those of you who are interested in passing. The Euclidean algorithm versus the... Actually, this year the Euclidean algorithm would probably beat the Red Sox. The Euclidean algorithm versus the trefoil knot. I will admit I have never seen the debate. I don't need to see the debate. It's a slam dunk. Euclidean algorithm clearly wins. Okay? The Euclidean algorithm is one of the most important algorithms in mathematics. How many of you have heard of the Euclidean algorithm? Anybody know why we care about it? Okay, so what I want to do today is I want to analyze the Euclidean algorithm, talk a little bit about why we care about it, and talk about how it actually runs significantly faster than you would expect. And I'm going to use this as a proxy to be significantly lazy later in the semester. I just want to make sure we're all on the same page. This is a 300 level class taught by myself. There should be a reputation on campus now. I've been here long enough that I teach classes at a high level, at a fast pace. I expect you to do a lot of work. I do, however, understand that this is a first course in the subject. Okay? I am not going to prove in great detail, in full detail, all of the results, all the classic theorems in linear programming. There are certain algorithms in linear programming that are key to the subject, and they work efficiently. I am not going to prove how well some of these algorithms work. I will prove they terminate, but I will not prove that they terminate in less time than it would take for the universe to die a heat death. Okay? What I will do instead is I will talk about the Euclidean algorithm today, and I will make a really bad specialist argument by analogy and say, look, the Euclidean algorithm runs a lot faster than you might expect. Maybe this algorithm that we'll see later in the semester runs a lot faster than you might expect. Keep taking math and you'll see that. Okay? So this is why we're going to be spending the time today doing the Euclidean algorithm, because it's going to be a really good motivator for what we're going to see later, and the fact that things can run significantly faster than you would expect. This is different than the other algorithms we've seen. When we looked at Horner's algorithm for ways to evaluate a polynomial quickly, or we looked at fast multiplication for matrices, the Strassen algorithm, these algorithms ran faster than the naive brute force algorithm, but we were already doing something clever. And then we were trying to analyze, well, now that we've done something clever, how long will it take to run? We're going to do something else now. We're going to do some algorithm which will be fairly straightforward. There's going to be a trivial way to estimate the runtime, but it turns out it runs much faster than you would expect. Okay, so Euclidean algorithm. So if x and y are positive integers, relatively prime, and we often write that as xy equals 1, then there exists a and b such that ax plus by equals 1. Can anybody name a class where you might see something like this? Abstract algebra. Okay, I'm not positive because I've never actually taken abstract algebra, as I've said, but when I teach abstract algebra, I do put that in. All right, this is extremely useful. Where do you use this in abstract algebra? When I say this is useful, I mean the Euclidean algorithm, not abstract algebra. Where do you use this in abstract algebra? Silence. Bunch of your homework problems. Okay, it should be useful for more than just cookbook. When you're understanding the group, say, Z mod and Z, when you're trying to figure out, do you have inverses? Well, put in star. Right. When you're trying to figure out, do I have inverses, something like this is extremely useful. And you can talk about maybe y is going to be a prime or something like that. So, if you haven't taken abstract algebra, no worries. Okay? So we want to find a and b such that this equals 1. This in turn has numerous applications in cryptography in one of the most famous algorithms of all time, RSA. So one of the reasons RSA is so useful is not just that it's pretty secure, but it's also very fast. Okay? It's not going to take you 2 years to encode and decode a message. You're going to be working with huge numbers. You're going to have to find inverses of numbers. And this allows you to find multiplicative inverses. So this is the same as ax is congruent to 1 modulo y. And so what it means to say ax is congruent to 1 mod y is the difference between this and this is a multiple of y. Here, what would that multiple be? Almost. The multiple would be negative b, right? Because I'm bringing the by over to the other side. So in an abstract algebra class, you'll study congruences like this all the time. You have all seen this. Approximately what time is it now? Approximately what time is it? 10 o'clock. What time will it be in 5 hours? I'm hearing 2 different answers, which is, it's okay to hear 2 different answers, but I'm not hearing the 2 different answers that I will accept. What time will it be in 5 hours?
15.
15 is one of the acceptors. And the other one, yeah, military time. Drop and give me 30 answers. Okay, 15 or 3. So obviously most of us do not believe that 10 plus 5 equals 3. But 10 plus 5 does equal 3 on a clock. That every time you go around, every time you go up by 12, you reset. And so 10 and 15 differ by a multiple of 12. They differ by one of the nicest multiples of 12 you can, 1 multiple of 12. Okay. So the Euclidean algorithm, it turns out when you're doing RSA to encode and decode, you need to find multiplicative inverses quickly. And the Euclidean algorithm allows you to find them. So over here, I have not stated the Euclidean algorithm in full detail. I have just said if x and y are positive integers relatively prime, then there exists a and b such that this is true. And we can find a and b very fast, bless you, and constructively. I'm deliberately being vague here to keep as a little bit of suspense exactly how fast they are and how constructive they are. But there's really 2 statements here. The first is that a and b exist. The second is once they exist, you can find them, and you can find them very fast. Okay, instead of saying x and y equals 1, instead of saying x and y are relatively prime, we could modify this and say x and y are multiple, x and y, their greatest common divisor is 2, 3, 4, 5, 6, 7, or more generally d. And we have a very similar theory for when x and y have the greatest common divisor d. This is not a number theory class. This is not an abstract algebra class. I'm not going to go into those cases. I'm going to just assume x and y are relatively prime right now. That's the case that we really care about. For this course, we don't really care about the other stuff. Okay? So the first question is existence. Can we find or prove, can we prove a and b exist? So again, it's almost a cookbook recipe of questions to ask when you're given anything in mathematics. Very first question you can ask about something is, does it exist? What's the next question? Is it unique? After that, what can you ask? Let's say it's not unique. How many are there? And after how many are there, is there a canonical representation? Okay, canonical, that's hopefully the new question for the day. All right, is there a representation that is more natural than all other representations? If we think about something like this, assume there exists an a and a b. Do you think a and b are unique? Or do you think if a and b exist, there will be more than one a and b? What do you think? How many people say if A and B exist, there's only one choice? Okay. How many people think if A and B exist, we can find other A and B that work? So we want to then tweak A and B a little bit. So imagine uniqueness. So imagine, say, A naught x plus B naught y equals 1. Consider A naught plus alpha times x plus B naught plus beta times y equals 1. We want to see, can we find an alpha and a beta such that this will also be a solution? So we get A naught x plus B naught y. Well, that's good. What does that equal? That equals 1 plus alpha x plus beta y. So we want this to be 0. Can we find a choice of alpha and beta so that this will be 0? So can we find a choice of alpha and beta? Come on, there we go. Can we find a choice of alpha and beta such that this will be 0? Okay, yes.
If they're relatively prime, then only 0, 0.
If alpha and beta are relatively prime, then only 0, 0. But what if we don't require them to be relatively prime? Can we come up with choices of alpha and beta to make this 0? This is a great time to be a smartass. Can somebody give me a choice of alpha and beta that would work? Yes. All right, 0, 0 is too much of a smartass because if you take 0, 0, you have the same solution you started with.
Y and negative x.
Y and negative x. That would work. Anything else? So if I put y and negative x, they'll cancel. What else could I do? Yes? I can put n's in front of them. So in fact, you've just given me infinitely many examples. So this leads us to a canonical representation. If I have something like this, I can probably pull down A and B to make them live in a certain region. Right? I can keep subtracting things off, and I can probably normalize so that they don't get too large. Okay. Any questions about something like this? This is also another way to lead into what we're going to be doing in linear programming. We're going to be looking for solutions. And frequently, we'll have many different solutions that will work. And we'll want to somehow move among different solutions and then choose a solution that has a certain key property. So this is, in linear program, is going to go from feasible to optimal. So if you have a bunch of constraints, you should satisfy the constraints. Right? You know, one of the constraints if you're an airline is if a plane is flying from Boston to Los Angeles, it is not simultaneously flying from Las Vegas to Miami. Right? And you cannot come up with a schedule where the same plane is doing 2 different routes at the same time. Okay? You've got certain feasibility issues that have to be held. And so what we're going to want to do when we do linear programming is we're going to want to look through the space of feasible solutions. And from all the feasible solutions, we're going to want to single out either one or a subset of solutions that are in some sense best. And those will be what we'll call the optimal solutions. They'll maximize profit, they'll minimize cost, something along those lines. So again, for those of you who do not like abstract algebra, for those of you who do not like number theory, there is a reason why I am doing this problem and I'm spending so much time on this. This is a great way to introduce the idea of searching through spaces, where we have multiple solutions and we want one that's canonical, we want one that has better properties than others. Okay? All right, so any questions on this part over here? All right, so we now know that if there is a solution, there will be infinitely many solutions. All right, this is very similar to a lot of things in linear algebra when you're looking at matrix equations. What are the possible solutions to a matrix equation? How many solutions can you have? Yes? 0, 1, and infinitely many. And so over here, we either have no solutions, or as soon as we have one solution, we have infinitely many solutions. Okay. So let's prove a solution exists. Proof a solution exists. So there's lots of different ways of trying to do the proof, of trying to arrange the algebra. So consider all ax plus by, and I want a range for a and I want a range for b. What do you think my range of a should be? Where do you think a should live? I'm sorry? Integers? Positive integers. Do I have to consider all positive integers? So we just showed before that if we had a solution, we could add something to a, subtract something to b, and get another solution. Yes?
A should be less than y.
A should be less than y with 0 less than or equal to a less than y, 0 less than or equal to b less than x. When I look at a restriction like this, if I increase things, I can just play my games. It should be enough to consider something like this. Now, unfortunately, when I do this, I may not be able to solve ax plus by equals 1. I'm going to weaken my goal. I'm going to try to solve ax plus by is congruent to 1 mod xy. And what this means is, that means the difference between this and 1 is a multiple of x and y. So for example, imagine I have ax plus by equals 1 plus 317xy. All right, as soon as you see a number like 317, what do you think? Random. Right? I could have also used 2014, 24601, 1701, 1792. I'm just trying to illustrate here, it does not really matter what this is. So imagine I have a solution like this. I can shift and get a solution to ax plus by equals 1. How could I shift? What could I study? So I want to tweak either a or b or both. I claim you can get there by just tweaking just a. Any thoughts? So I'm too large by 317xy. I need to make this left-hand side smaller. What can I do to make the left-hand side smaller? Yes?
Decrease a by 317y.
Excellent. I could then study a minus 317 times y x plus by, and what will that have to be? Has to be 1. Almost nobody would actually change b. We all seem to like to change a because it comes first. Doesn't really matter which one you change. Could I have decreased a by 300 and decreased b by 17? Yes. It would be foolish to do so, right? This is the easiest way to do it. This is a general theme in mathematics. Rather than solving the particular problem you want, is there an easier one to solve which you can then use to hop to the solution you care about? And instead of trying to find that it exactly equals 1, if I can show it differs from 1 by a multiple of x and y, I can then correct. So all I have to do is I just have to get ax plus by to be a multiple of, to be 1 plus a multiple of xy. And then I'll just do a little local movement. Okay? Everybody happy up to here? So now, how many possibilities do I have? I'm considering all ax plus by. A is between 0 and y, can't be y. It's between, b is between 0 and x, can't be x. How many possibilities do we have? So how many possibilities do we have? Have xy possibilities. How many possibilities do I have for something to be congruent to modulo xy? How many options are there? How many residues are there? How many targets are there? How many congruences are there? It could be congruent to 0, 1, 2, 3, all the way up to xy. We have xy possibilities for ax plus by. Also, xy residues modulo xy. If you think about it, on a clock, how many possibilities are there for the hour on a 12-hour clock? How many possibilities are there on a 12-hour clock? 12, right? My kids can get this one, right? They don't understand necessarily why they want to get this one. Right? If I give you a 15-hour clock, how many possibilities would there be? 15. So there are xy possibilities, and I have xy values of this as I range over all a and b. So I have two possibilities. Either I luck out and one of them is 1 plus a multiple of xy, or that never happens. Okay? Those are the two possibilities. So case 1, sum AB give ax plus by is congruent to 1 mod xy. So this means that ax plus by is a multiple of xy plus 1. Are we done? Did we find an a and b such that ax plus by is 1 plus a multiple of xy? Yes. Case 1 is trivial, right? Done. Okay, that's the trivial case. What's the harder case? You don't find a solution. Never get ax plus by congruent to 1 mod xy. Can this case happen? We're trying to prove the Euclidean algorithm. We're trying to prove that we can always solve this. So can case 2 happen? No. So we have to show somehow that case 2 can't happen. Question?
No,
OK. Does it begin with P or D? OK. What's your idea?
You assume that it never happens and then you use the pigeonhole?
So we're going to use the pigeonhole principle, the box principle, Dirichlet's box principle. I prefer to say the Dirichlet's box principle because I always misspell the word pigeon. I don't think you're supposed to use a D in it. How many of you have heard of the pigeonhole principle? The pigeonhole principle is one of the most powerful ideas in all of mathematics. It says the following. Imagine you have n plus 1 pigeons, you have n boxes, and you have a pigeon gun. Okay, so you load n plus 1 pigeons into your pigeon gun, and you start shooting the pigeons into boxes. Okay? It's a nice gun. It gives them a nice gentle ride. They're cushioned. No pigeons will be harmed in this thought experiment. Okay? So you shoot the n plus 1 pigeons into the n boxes. Is it possible that every box has either 0 or 1 pigeon in it? You're shooting n plus 1 pigeons into n boxes. No, because that can account for at most n pigeons. There's got to be at least one box that has 2 pigeons. Another way of looking at this is at least one box must have at least the average number of pigeons. And the average number of pigeons here is a little bit greater than 1, so there has to be one box that has at least 2 pigeons. Does there have to be a box with 3 pigeons? No. Do there have to be 2 boxes with 2 pigeons? No. But there has to be at least one box with 2 pigeons. So by the pigeonhole principle, we have A, B, A tilde, B tilde, such that AX plus BY equals A tilde X plus B tilde Y plus some multiple of X and Y. And what this means is, look, this has some remainder modulo xy. This has the same remainder modulo xy. The only way they can have the same remainder is if they differ by a multiple of x and y. Okay? And without loss of generality, let's assume oh, I'm sorry, I put the tilde in the wrong spot here. Let's assume b is greater than b tilde. And then if b equals b tilde, what do we need to do about a and a tilde? So if b equals b tilde, turns out that will imply a has to be a tilde, and they'd be the same thing. So I'm not going to really go through that case. I'll let you think about that. All right, so we've just shown in case 2 that imagine we don't hit the residue class of 1. So if we don't hit the residue class of 1, then one residue class has to be hit at least twice. Because we have xy minus 1 residue classes remaining, we have x choices, so one of them has to be hit at least twice. So we can choose a tilde, b tilde, such that they have the same remainder when we divide by xy. So what we get now is a tilde minus a times x. I'm sorry, do I want to do it this way? A minus a tilde times x plus b minus b tilde times y is some multiple of xy. Okay, so we've subtracted off. We have now a relationship like this. We're trying to get a contradiction. I'm assuming b is greater than b tilde. So what do we know about this number? I'm sorry? It's non-negative. So 0 is less than b minus b tilde is less than what? X. Who has a really good memory? Okay, who has an okay memory? All right. What are we assuming in this problem? Everything's an integer, but we're assuming a certain relationship about some integers in the Euclidean algorithm. We're assuming something, we're trying to get that there exists in a and b such that ax plus by equals 1. We're assuming x and y are relatively prime. At some point, that should probably enter the argument. Right? Usually when you have assumptions, when you have givens, they're there for a reason. The results typically are not true if they do not hold. So as an example, choose x and y that are not relatively prime, and you'll show that you cannot have ax plus by equals that. So for instance, if x equals 4 and y equals 6, can we solve a times 4 plus b times 6 equals 1? No. This is always going to be a multiple of 2. Right? The givens are there for a reason. So when we come back over here, let's look over here. This is a multiple of x. This is a multiple of x. What must be true about this? Multiple of x. So we get b minus b tilde times y equals my plus a minus, I'm sorry, I guess minus a minus a tilde times x. So x divides b minus b tilde times y. Can x divide b minus b tilde? No. X cannot divide b minus b tilde. It's too small. So x has to share a factor with y. Therefore, x shares a factor with y as b minus b tilde is too small. And that's a contradiction. Okay? So again, at some point you need to use the givens. And we use that to get a contradiction. The contradiction is that x and y are not relatively prime. All right, so there's a lot of stuff going on in this proof. So I'm introducing you to a lot of abstract algebra. This is actually a good thing. Most of you, if you're going to be a math major, will have to take abstract algebra. It is unusual to complete the math major, it's not unheard of, without taking abstract algebra. So you can look at this, if you want, as here's a little bit of an advertisement for what you could take later. For those of you who have already taken abstract algebra, here's a little bit of a dividends of something you've done. Here's why you might care about that. Okay, so we've now proven that if x and y are relatively prime, we can find a and b such that ax plus by equals 1 plus a multiple of xy. From that, we can then correct and get to ax plus by equals 1 by just shifting things accordingly. I'm not going to bother going through the details. You can always find choices of a and b such that a is between negative y halves and y halves, and b is between negative x halves and x halves. That's the canonical way to have your representations. I'm not going to bother doing that. I'm just going to leave it as this. So is everybody happy that the Euclidean algorithm has been proved? OK. We now have an algorithm. It should be instinctive now. What is your first question once you have an algorithm? I'm sorry? How can we use this? OK, related to how can we use this? Can we use it? How fast is it? If the universe is going to die a heat death before it finishes running, it's not useful. Well, and the next thing is, this is related to how can we use it. Can we find a and b? Is this method constructive? Yes or no? Is it constructive? Does it tell us how to find a and b?
You said so.
I said so. William says it's absolutely fine for you to paint our house. No need to check on that. Yes, is it constructive?
Not really, but there's only a finite number of possibilities, so you could technically go through all the x, y.
So kill the not really.
Yes.
Yes, it's constructive. The algorithm says the following. Look at all possible a and b, where a ranges from 0 to y minus 1, b ranges from 0 to x minus 1. Keep trying pairs until you get something that's a multiple of xy plus 1, and then just correct downward. It's constructive. How many things do you have to try? A lot. OK. So when I teach Calc 3, I will say things like a lot. I'll say consider a nice function. But in this class, I want to quantify a little bit a lot. How long? How many checks? Worst case scenario. Worst case, check how many things? Yes? XY. Might be able to do a little better. It's probably not 0, 0. So if you want, you might be able to improve this from xy to xy minus 1. It's not really much of a savings, OK? This is long. So as x and y get very, very large, let's say x and y are of size 10 to the 200. And in applications, they will often be this large or larger. Number of steps? Approximately how many steps? 10 to the 400. All right. This calculation needs to be done at least one time during the semester. Let's do it right now. Let's calculate number of seconds in a year. How many seconds are there in a minute? Try again. How many? 100, yes. There's 100 seconds in a minute. How many minutes are there in an hour? 100. How many hours are there in a day? You could probably get away with a 10 because we've been so bad here, but 100. How many days in a year? 1,000. 3, 4, 5, 6, 7, 8, 9. This is a little bit of an overestimate, but it's not horrible. All right? So 10 to the 9th seconds roughly in a year. How many operations can your computer do in a second? Really good computer.
3 million-ish.
OK. Number of computations per second. Hell, I'll be nice. I'll give you 10 to the 20. All right? I'm going to be really, really nice today. How many subatomic particle doohickey whatchamacallit thingamajigabobs do we have in the universe? Roughly. 10 to the 80, so 10 to the 100. Number of objects in universe will be about 10 to the 100. So I will assume every object in the universe is a supercomputer capable of doing 10 to the 20 operations per second, devoted exclusively to your use. I have taken econ classes in college, and I have learned how to make reasonable assumptions. Okay? So I'm getting some dividends from that now. Okay? So every subatomic doohickey in the universe is a supercomputer devoted exclusively to your use. In 1 year, how much can you do? Can do how many things? How many years do you need? How many years do you need? 10 to the 200 and what? I think 71. Right? Even if we have some kind of square root cancellation, we only need to do 10 to the 200. We would still need 10 to the 71 years. We are at the level of heat death of the universe many times over. Okay? It's a finite calculation. Theoretically, it's been solved. For practical purposes, this is useless. And we will have numbers in RSA that are this large. Right? So even if somehow it's only enough to just check the value of A, and when you check a value of A, you immediately know what value of B should work or not work, which is not unreasonable. Because if you have a value of A, you just try to see is B an integer. You just solve the equation. B equals, what would it be? Well, I won't bother writing. So it's not unreasonable to suspect maybe we only have to vary A, and then for each choice of A, we either immediately find out B works or B doesn't work. Even if that was the case, the 10 to the 400 becomes a 10 to the 200. This becomes a 10 to the 71. So if you want to figure out, it goes billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion. You could try to figure out exactly what word you would need to represent exactly how bad of a computation this is. So for all practical purposes, this is useless. Okay? So again, I am not saying abstract algebra is useless. Okay, I've got to be very careful. I want to make sure you get the right lesson. In abstract algebra, frequently all we need is the inverse exists. If the inverse exists, it's a group. Do we have to find the inverse? No, we just want to prove the inverse exists. So for a lot of things, we just need to know the inverse exists. That is not this class. This class, we need to find solutions. And that's one of the reasons why I want to describe this algorithm. Okay, so now claim Euclidean algorithm runs in logarithmic time. And so what we're going to do is the following. Here is a procedure to find the A and the B. Procedure to find A and B, given x and y relatively prime. So I'm going to write y equals a1x plus r1. I'm going to see, and I'll assume here that x is less than y. I will assume x does not equal y, because otherwise this is not a difficult problem. So I'll assume x is less than y. I look at how many multiples of x I can take so long as I stay below y, and then r1 is the remainder. So this is just long division. So 0 less than equal to r1 is less than what? How large can the remainder be? It can be at most x. In fact, it's got to be a little bit less than x. If it was as large as x, we could have increased a1 by 1. Now it turns out that if x and y are relatively prime, x and R1 are relatively prime. Why? Imagine 5 divided x and 5 divided R1. Then 5 would divide this and 5 would divide y. So x R1 is the same as yx. They're still relatively prime. Lather, rinse, repeat. Now I write x as a2 R1 plus R2. And what do I know about how large can R2 be? Less than R1. Again, R1 is A3 R2 plus R3. How large can R3 be? How large? I'm sorry? How large can R3 be? R2. And so we keep going. And we'll have R1, R2 is the same as XR1. Every time we apply this, we know the remainder gets smaller by at least 1. So remainder decreases by at least 1. So runtime, worst case scenario, is worst case how much? Worst case, how long will it take to run? X. Or maybe x minus 1. I don't really care about x versus x minus 1. If x is of size 10 to the 200, I don't really care if it's 10 to the 200 or 1 less than 10 to the 200. I'm screwed in both cases. Okay? It will terminate. And it's a nice exercise in algebra to go through and see that at the end of the day, you will actually have an expression. OK, now I want to show you that it runs really fast. And here is the claim that makes the Euclidean algorithm such a great algorithm in mathematics. So lemma. Rk plus 2 is at most half of Rk. So what this is saying is every 2 iterations, I decrease by at least a factor of 2. Over here, there we go. Over here, every 2 iterations, I decrease by at least 2. There's a huge difference between decreasing by 2 and decreasing by a factor of 2. So if I do this 10 times, I decrease by at least 10. If I do the other one 10 times, I decrease by a factor of at least 1 over 2 to the 10, I'm sorry, 1 over 2 to the 5th, or a factor of 32. So this is going to lead to logarithmic time. And so if this were true, then the number of steps is at most something like 2 times the log base 2 of x. Yes?
Wait, sorry, did you say that that means that every 2 steps it decreases by a factor of 2 or by?
By a factor of 2. Rk plus 2 is at most half of Rk. So every time I apply the 2 consecutive long divisions, my remainder is at most half of the remainder 2 steps ago. So if I do it 4 times, I'm at most 1/4. If I do it 6 times, I'm at most 1/8. If I do it 8 times, I can't multiply that high, but you get the picture. So why is this the case? Proof. Case 1, Rk plus 1 is less than or equal to 1/2 Rk. If Rk plus 1 is less than or equal to 1/2 Rk, do I get Rk plus 2 is less than or equal to 1/2 Rk? Yes. Done as Rk plus 2 is less than Rk plus 1. Case 1 is boring. All right. Case 2, that's interesting. Case 2. Rk plus 1 is greater than 1/2 Rk. And this is a very natural way to divide things. What does it mean if Rk plus 1 is large? Well, I have Rk equals a k plus 1. Let's see, I want to make sure I do it the right way. The index here is wrong, so don't write it down. Okay, I want this to be k plus 2. Rk is ak plus 2, rk plus 1, plus rk plus 2. I hate having to erase this, but. So let's look and see what this means. So we have rk equals ak rk plus 1 plus rk plus 2, and we know two facts. We know that 1, rk plus 1, is greater than 1/2 rk, and we know rk plus 2 is less than rk plus 1. Well, if this is greater than 1/2 rk, what's the only possibility for ak plus 2? What does ak plus 2 have to equal? 1. This is more than half of rk. If I had a factor of 2 here, this would already exceed rk. So because this is more than a half, I need ak plus 2 equals 1. So therefore, ak plus 2 equals 1. Therefore, rk plus 2 equals rk minus rk plus 1. Well, if this is more than 1/2 rk, the difference is less than 1/2 rk. And that completes the proof. Right? There was a lot of stuff here. Okay, in terms of actually doing the simplex method, in terms of actually doing linear programming, everything we did today is useless. Okay? But in terms of getting a sense of the type of calculations we're going to do, this is very useful, and in my mind, it's one of the best transitions between the theoretical mathematics that a lot of you have seen and the more applied mathematics that we're going to start to really do in detail starting on Wednesday. This new perspective you have to adopt in terms of doing these calculations. It's not enough to have something that's theoretically doable. We need something that is doable in a reasonable amount of time. So I will send you more notes to read about the Euclidean algorithm. It is absolutely fine if you do not understand line by line everything here. Okay, hope that's still working. Okay, hope that was someone's phone. Okay, so it's okay if you do not understand line by line what was going on here. The idea, the general theme of how to go from a general solution to a solution with specific properties, that's important. We're going to be doing that when we go from feasible solutions to optimal solutions. Right. The other thing I'd like to do for this class is I would like to have a fun reading or a fun business problem each week that we'll discuss on Friday that's related to real issues in operations research. So in honor of my uncle who just passed away, who sadly adopted the wrong technology time and time again, I thought a good first choice would be VHS versus Betamax. Out of curiosity, how many of you have heard of VHS or Betamax? These are the old VCRs, video cassette recorders. And so there were two dueling formats that came out around the same time, VHS and Betamax. And it's fascinating as to which one won and why. And there's a lot of really good questions. I'm going to post some stuff to read in the additional readings. I'll give you a link on that. And then I want to spend a little bit of time on Friday talking about what we can learn about cases like this. It could be useful to you when you're doing job interviews. You might be interviewed by somebody who's old, who might actually remember the battles between VHS and Betamax. The other thing is these battles are still raging on right now. What do we record everything in for movies? What do we record movies on? What do we store them on? I'm sorry? DVDs are going the way of the dodo. Blu-rays or computers versus streaming video. And so, will we still have personal libraries in 10 years? Or is everything going to be on central warehouses? And so it's fascinating to see how things are going to be done. When I buy Blu-rays now, they actually throw in a DVD for free, which is wonderful because I can, well, it's better stop now. All right.